debounce on Tuesday next week. Sorry, I know you hate quizzes. Gotta do some quizzes. Haven't done a quiz for a long time, right? For a week or almost. A week is a long time. Yeah, I hope have learned something this semester. Is that too slow this semester? No? Do you think it's slow? I slowed down a lot, I think, compared to the previous semesters. We also added more tasks. I think we are going deeper instead of faster, which is good. So are getting any progress on the LCD display for the calculator thing? So the demo I sent to you guys, have you started working on that? Not yet? And it's really fun. I'm a very lazy person, and I'm thinking about adding a new task to it. I got excited actually. I was thinking, oh, this is so fun. If it works, it's gonna be so fun. I can keep working on this for the whole day. If I'm paid for $200,000 a year just working on this, I would just do it. Right? I would just do it. If I don't have to teach, if I don't have to write grants, mentor students, and all these things. I also like these as well, but digital is so fun. It's repeatable, and you make a mistake sometimes somewhere and it still works. So it's resilient to errors compared to other technologies. I send you the link of the video, and I want to talk about this really quick because this is not ideal. I just spent like 2 hours on it and starts working, and then I didn't polish it, but I know you can definitely improve it a lot. So the refresh rate is very low. That's why after I updated the switches, these numbers are still not changing. So you can see definitely you can make it better. It's because of the HDMI problem, so there's no audio. But you can see compared to other calculators, this is definitely not ideal because I always show something plus something. It's always the plus sign is always there. So I hope you guys can make it into so this interface should be very similar to the real calculator. If you don't put a plus sign over there, it shouldn't plus, right? It shouldn't assume that the user is going to do a addition operation. I just didn't change it as a variable. I just directly throw that plus sign as a character over there, so it always shows up. And also you probably have to increase the refresh rate. So every time I change the input from the switches, the numbers should be updated instead of just waiting for the cursor to come back and refresh it. This is a very easy change, right? You have done that already, right? So I changed it. It will do the addition. It will change the number over here. And since we don't have a lot of combinations, it's only 3 bits. So the lookup table or the translator's list of all the patterns definitely not that long. It's only from 0 to what? If it's unsigned, it's 0 to 3, only 4 entries. The largest positive number of each switch is only 011, right? It's from 000 to 011. That's the largest input you can give to the A's or B's. So the largest positive number will be 011. I mean, for tools, so we can start from this, right? So that's where I got started. You can start from this, but later on, you just start adding signs, add the tools complement. So you know the range, right? For the 3-bit battery number, it started from a -4, from -4 to +3, right? That's the range of the 3-bit tools complement. How many numbers? About 8. Pretty much 8 numbers. So there's 8 entries in the lookup table, so it's not too big. It's easy to program, and for the 4 bits will be a little bit longer, I think. The 4 bits is giving you -8 to +7, so you are having like 16 entries as the final result, right? Depending on the sign, the MSB, you can change the sign, you can add a sign to it, a little bit task over there. So given that, I'm gonna delay the assignment due date for the storage units to Tuesday instead of today. Homework 4, all right? It's gonna be Tuesday next week instead of today, right? And we have a little left over here we didn't cover, which is the memory, right? So the memory, how do we do a memory? And eventually you can see this is a IP. Okay, it's the IP. This is the first experiment working on the IPs in the Vivado environment. And you can see we bring in a ROM. I forgot what the B stands for. RAMs, whatever. So it follows the instruction, eventually grab an IP. So IP is a digital block. The digital block is the memory block, all right? So the memory block, when we are talking about memory, we think about the memories. It's just about the memory banks, right? Store data in there. But actually, it also has a lot of peripherals, like all the decoders and everything else, the clock, and a lot of digital circuits instead of data, just the data, right? So the IP is a block that will store the data into the 8-bit memory banks, into different entries depending on the size we want to define the memory to be, and also has clocks, has decoders, has all the peripherals. So this is blocks, the IPs block, right? So that's a diagram of shows all the pinouts, and we are not using all of them. You can see you can add a lot of functions to it, but we are only using a very simple clock with a very simple memory with a clock and an address. So and the output as well. So you can configure everything based on the interface. All these different modes, all the functionalities from the tabs you can define. Just follow these, and also you can give a depth, right? So how many entries you want the memory to have, things like that. Right, like these ones. And then this is the data file. So the data file is only the data for the memory, not everything. The memory also has peripherals, like I said, right? Clocks, decoders. And we cannot not really see it because this is really a IP block. So the design environment like Vivado, or in the future you can use probably on Quotas from Intel, the Ultra FPGAs. They all have all these IPs. Some of them are free. You can use them for educational purposes, but if you are using them for commercial purposes, you probably have to pay some money to the company, right? But these ones are available there for you guys to directly use them. After some configuration, and you eventually created a memory block has all these pins, right? So data out, okay? Clock. So A, I think, is just the A ports, B ports, but these are just A ports, right? The A ports has A pins for the port, so it's outputting an 8-bit data to the interface. Okay, to the interface. So clock is receiving a clock to trigger the output or to synchronize all the operations in there, and address as well. So you need an address to determine which entry of the memory you want to take out that memory from, and then send it to data out. Okay, these are all the ports. It's really simple memory: address, clock, and data out. That's it. You can see this is how you instantiate your memory in your top. You can see the my ROM. My ROM is the name of the memory. I think by default the name of the memory is called my ROM. I think that was from a setup somewhere, right? When you name it. Okay, I couldn't see it, but it's one of the steps that you name. You name it my ROM, so that's the module name of the ROM. So the ROM, it's read only, right? So you're not writing to it; it's read only. That's why it's called a ROM, read only memory. And you rename it as U. It could be DOT, it could be whatever UUT. You can name whatever you want in your top, right? And then these are the ports of the memory, and these are the ports from the top, as it makes certain connections. So the top will read these out and display it in the monitor. And here's an example, but I blocked part of it. You can see because this is a simulation experiment, so we are not having any actual physical ports to be connected to the FPGA. So we just have a myrom underscore TB and semicolon. We just end it right after the module name. We don't have a parenthesis with all the ports. There's no ports. It's just basically it's wrapping up the modules inside the top and then feeding the signal into the sound module within the top instead of receiving from the physical pin resources on the board. Okay, so take a quick look at it, see if you have any questions on this. What's that?
Canvas, you had to do Tuesday.
Tuesday for what? For
The 17th, the homework. That's when
for this one? Okay, yeah, I'm gonna change it to next Tuesday.
Are you going to have more stuff? Is that
No,
what you
no,
did?
I mean just this one, right? Just this one.
Yeah.
Yeah.
Okay.
Is that homework 4?
Yeah.
What's the due date on Canvas?
Tuesday.
The 17th.
Yeah.
2 days.
Oh, you already submitted.
Yeah.
Jeez, you guys are productive. That's great. Okay. If you haven't, you still have the time to modify it. Okay? I'm gonna change it to next Tuesday. All right. Yeah, I went through everything during the weekend, but didn't pick that up. Didn't pick that up. Okay, let's go to the UART one. Okay, we did a little bit of UART in the microcontroller class, right? So we all know that it's RX and TX, right? Just 2 ports, serial. And it starts with the what? With a pulling down of the TX, right? So the TX pulls it down to ground to start it. So here's a timing diagram. Okay, the timing diagram. So pull it down to ground to start it from the TX. Now let's look at the in class, okay? In class. We had a similar question in the microcontroller class, right? So we pull it down to ground to start it, and then stop it by pulling this up from the TX, okay? And it doesn't have to have a parity bit depending on your design and your needs, actually. But it's just looking at the timing, you just put whatever you have to put in there, right? And your receiver has to know it if you have a parity or not. But you can see it's from 8 bits with the start bit and stop bit. That's the whole protocol for the UART. It's a really old technology. It's slow, but pretty reliable, and it's just pretty much everywhere. You can even see it from the modern. So the modern RF modules, right? So 2.4 gigahertz modules. They got the RF signals and then the digital chip converted to UART, and you can interface with your microcontrollers, right? So that's a pretty popular port. And so as a digital designer, we should understand what's really going on. Like during the interviews of the digital design, very likely they will just let you guys, hey, write all the states or write the module for the UART TX module, right? It's very possible. As the NVIDIA interviews, like I saw one of the interviews in UCLA many years ago when I was a graduate student. I went there, and NVIDIA, they just gave people exams on the paper, like quizzes. So you guys already have been doing this a lot, right? Just give you a paper and let you guys write down all the Verilog code for digital modules or interfaces. Right, that was a super long line. That was, when was that? That was probably 2013, 2014-ish, I think. Right, so the Broadcom and NVIDIA, these were, and also now as well, the super popular companies recruiting digital designers, computer engineers. And so that TX and RX modules, we can just design everything from scratch. I can imagine there will be, doesn't like any other digital circuits, simple digital circuits, right? So this will be probably eventually hundreds of gates, eventually, just from this short script, right? Eventually the UART block will take a little area on your chip, but it's taking some area that I can see, it's visible, right? You can see it from the microscope if you are looking at the die from the top. And so this is the module here, how you describe it in the hardware. And imagine that you have to, it's basically that you send all the data bits one by one, and you start with what? With the start bit, right? LSB first or MSB first for the data? It'll be on the quiz in the future or midterms, right? So these are all these key points for the important modules. So after the start bit, is LSB being sent first or MS being sent first? LSB being sent first. You can see D0 is here first, right? So in that case, when you are forming the whole data or the message to be sent, I mean, start bit is 0, there's no difference compared to a data bit. It's just a 0, right? 0 is 0, 1 is 1. So to form the data in UART TX, you basically do a concatenation, okay? Because the data is a vector. I'll let you guys take a look at it. All right, so here's the data. And you form the data by doing this, 1 and 0. Okay, so which is LSB, which is MSB? Which one is the LSB after the concatenation? Which bit is LSB? Definitely on the right hand side, right? Okay, so 0 is LSB. It's actually the start bit. And the data has its own LSB. The data is 8 bits, right? So I have the data over here and then put it up. So you just do a concatenation, use a concatenation. You put the data in the middle and then starts with a 0, which is being sent at the very beginning. How do we know that? I mean, how do we know this 0 will be sent first? We just got started, don't worry about that. But next time we should be earlier, right? Should be earlier. Because I just wasted a lot of time to talk about the homework due on Tuesday this week. Ask for some refund from the chair. Ask for Dognali to get some refund. All right. So this is about the UR module, right? My question was, because the UR module requires 8 bits of the data, and it starts with the putting down the put down data 0 bit and stops with the 1 put up bit, right? So the way we send it, we form the message is one of the questions on the in class paper, right? So the way we form that data, the message is that we use a concatenation. We put the data in the middle, and then we wrap it with the starting bit and stop bit. So the question is, how do we know this starting bit will be sent first? Can you control it? In your module, you guys are digital designers, right? The UR module is going to operate in the way that you design it to operate. Different from the microcontroller class. We just have to use it, whatever they design, right? So now we design everything. We can modify everything. We can even insert some bugs into it for some purposes, right? Yeah, that's why some national security stuff, the defense companies who are making chips, they do not want contract this out to other countries, right? You couldn't see it. They are being fabricated. It's just one single or a couple of lines in a Verilog will synthesize into several transistors into a chip that you couldn't see. You couldn't really tell. You have done VLSI, right? see all these traces and wires. How could you know that transistor is sending out security data or privacy data, private data to someone else? It's a little circuit. You can modify everything. Okay, and other people couldn't even tell, because if they purchase that physical chip, and there's no way that they can really see what's really happening over there. Okay, so you put a 0 here and 1 here and put the data inside, and when you are sending bit by bit, you are actually using an index, and your index starts with 0. See? Starts with 0. So when you access all the bits in this data message, 10 bits message, it starts from index 0, which is the one on the right hand side, because after concatenation, this becomes the LSB. So it starts from here, and then you increment your index one by one, so you can send out every single bit. It eventually reaches the MSB, which is the stop bit. We'll put it up and then it's going to stop the transmission. Okay. Another question. So just assume that you guys are the designers, digital designers, who are designing these modules, TX and RX. Right? Now we are talking about TX. So the question is, I mean, zeros are zeros, ones are ones. How could we know that the starting bit 0 is the starting bit instead of a data bit? How could we know that? Or how the receiver knows that? It's just toggling, right? Just square waves as a digital message, right? It's going up and down, right? So if you think about that, you start the transmission at a certain point, and then what you're going to see is just basically, let me show you. One of the examples I think is a good one to look at. Course projects. All right. So just look at this kind of data here. A lot of times doesn't really tell you whatever the data is. So for example, these ones, right? So if you have a lot of ones over here, so if all the ones are just next to each other, you couldn't even see the data one by one. They're just the one single one over there, right? Also for zeros as well. So you're not really seeing anything. It's just all zeros. So the thing is, how could you tell that there are 8 bits of data and starting with a 0 and stop at a 1? How could you tell that? If the TX, the transmitter, is sending the data, right? The transmitter is sending the data. How do we tell which bit is starting bit, which bit is data bit, and which bit is stop bit? I want you guys to think about it. What are the solutions to it? If you guys are the very beginning inventors of the port, right? What's the strategy to figure that out? It's a bunch of 0 and 1s, right? And how could the receiver know how many data bits are in there, and where to start with and where to end with? To start with.
Because the data will only be like 8 bytes.
8 bytes, yes.
We'll be able to know when the light starts.
Cool. Yeah, so you can count, right? Count. But when you count, what else you still need for that counting? Like when you are sampling, right? So you have. Let me show you. If you don't tell people, how could you know this is like a 8 data bits and 1 stop bit and one start bit and 1 stop bits, right? Just like a rising edge. Yes, you can count, but except that, what else you have to figure out? What else? The bell rate. You have to know when to sample it. So what's the time point to sample? And then you count. Every time it samples, you count, right? So the bell rate. So which means, looks like this is a rising edge. right? Only one rising edge. But if you define the baud rate to be a certain baud rate, for example, the most popular one for UART, it's 9600 bits per second. So we know that the bit rate of this data frame or the message has 9600 bits per second. So depending on the time over here, if the time is 1 millisecond, for example, how many data points we have during this time frame? How do we calculate it? 9600 per second times 10 to the negative third second, right? Cancelled. How many data points in here? 9.6 bits. It's actually only 9 bits, right? 9 bits. Right? The last one is not a intact bit. It's probably just half. So when you sample it, right? You do a rising edges. The clock is sampling all everything. That's your bit rate, right? Every rising edge or negative edge doesn't matter. Depending on your design, you sample a bit each time, right? That's how you know it. So the RX and TX, their baud rate setting has to match. This is one of the most common problems when people play with Arduinos, right? So if your baud rate of the monitor is set up at 19200, but your code is setting the baud rate at 9600, you are getting some error code because these are the ASCII code being sent to the UART monitor will be something else, right? Depending on the different baud rate. So that's something you have to know. The baud rate has to match. And so for your UART design, your module, it's better to leave that as a variable so you can always change it depending on the user's needs from the top. And I mean, in software, you can write in the C code to change the baud rate, and I believe there's a mux or something else being put in there to let the user to change the baud rate. But for the hardware, we're not dealing with software, so it has to be changed in the hardware, and then you synthesize it. So it has to be synthesized into your hardware. It's different. All right. So the module itself, for the transmission, I have the state diagram over here, and also has a drawing, shows the ports, and the message has 0 as a starting bit, 1 as a stop bit, and 8 bits data in the middle. And the variable holding this one is called TX data in the code. That's the 10-bit data. You can see it's over here, the TX data. So it's the 10 bits, right? And TX bit, right? So TX bit is every single bit from the TX data message. So it's taking out every single bit each time, and we increment the index one by one until it reaches the MSB. And the TX bit is assigned to UART TX, which is a port in the TX module. It's at the bottom, so it's always assigned to this guy. It's a port because this guy is a port, so you are not modifying the port in your procedural assignment in the always block. We don't usually do that. So what you do is you directly give it to an intermediate variable, which is called TX bit, and you always assign the TX bit to the port at the bottom using a assign statement over here, right? And the way it works is really simple, even though it looks long, but actually it's super simple. It's basically just a counting. So sometimes it's counting, sometimes it's clear the counter. So starting from the ready state, right? So the ready state. So there are 3 different states. 3 different states in this TX module. Okay. So for the ready state, we give a 0 to the index. So it's starting from so let's make sure the index from the taking out the data bit, the TX bit from the TX data message to 10-bit message, taking out the MSB first, right? and the timer, clear a timer, and the TX bit, give a 1 to the TX bit. So remember, the TX bit is directly shorted to the port of the TX. Okay, so giving a 1 to it is necessary. Could you tell me why is that? Here, why at your ready state, the very beginning, you give a 1 to the TX bit. So the TX output, right? So it's just a one TX. So it's basically giving 1 to it. It's not a message. It's just a 1, right? Why we want to give a 1 to it at the very beginning?
Make sure there's no like, because it's the stop bit, so it just stops in the other data.
It's like a standby, right? Standby. It's waiting. It's ready to do the transmission after that state. So it, put a 1 over there. So whenever your message comes, it has a room to put it down, right? So it's a 1 always at the very beginning, and whenever the message arrives, like this one, the message over here, here, the LSB over here can put it down, but the LSB is a 0. So taking out the first one will pull it down from 1. So you can see a pulling down activity over there to start the transmission, right? So the RX knows, hey, transmission starts because there's a falling edge. And send, if send is 1, so which means, so that's the input port for the TX control unit, and that one is provided by the top module. So it's like a flag, right? So it only starts the transmission whenever send is 1. It's just a flag from the top, like command, right? If this is not on, don't do anything. So the top has a certain control over that transmission by using the send flag. So you can see if the send is 1, the send bit is 1, I form the message by putting a 0 and 1 at the two sides, two terminals of the data, and then I move to the next state. If send is not 1, it will never get into the next state because this is underneath that if statement over here. That makes sense? It has to be 1 first, then it will start moving to the next state. So whenever send is 1, which means the command from the top module allows that the transmission to get started, right? And it goes to the load bit. It's loading the bit. So load the bit. So what this one does is, whenever the timer reaches the baud timer, we'll talk about the baud timer in a bit. So whenever it reaches the baud timer, even though it's already in this state and it's synchronized to the clock, it's running at 100 megahertz really quick. Just keep checking really fast. Keep checking, right? Keep doing that. But being delayed by this baud timer, which is a count. The baud timer is a count over here. Is one of the questions in class, right? So the baud timer is a count, and it's 100 mega divided by baud. The baud is a number, which is 9600, right? So it's asking you guys why use the baud timer divided by baud will give you the desired counts for this time delay over here. Think about it. It will be on the quiz. Okay, it will be on the quiz. So why is that? Exactly, but how that works, right? So it's 100 million, right? That's the clock frequency. What's the unit here? What's the unit of this guy? Counts, right? So this is the original counter we have. So it's counts per second. Okay? So what is 9600 though? Divided by 9600, right? Bits per what? Second. So eventually this is cancelled. So we're having 100 mega divided by 9600. What's the unit? Counts per what? If that makes sense, does that make sense? Counts per bit. Why do we need that dimension?
So how many counts we need to give a one for to register
To reach that baud rate, right? Does that make sense? How many counts we need to count up to in order to wait until we send the next bit. Alright? So that's actually counts per bit. Yeah, definitely the desired final result is going to be bit per second, which defines the baud rate. But we don't have that timer, right? We only have a 100 megahertz clock. So we have to use the counts per bit to do the job. And so whenever it reaches this low bit state, we don't want to load, or we don't want to take out a bit from the message until it reaches that number of counts, which is the variable called baud timer, right? So the baud timer is the number of counts we want to count to up to, and then we take out one data from here. See, it's the TX data with the index over there, so it's being taken out and then being sent to the TX bit, which is exactly the TX port, because this is being shorted to the TX port over here. Okay, so after this number counts, I take out one bit and send it to the port to reach 9600 per second. All right, and then I increment your index. If it's not reaching that timer yet, just keep counting up. Let's keep timing up or counting up. So the question is when we so whenever it reaches that count, I'm ready to send one bit. So I'm taking out one bit and send it, and the state goes to the send bit state. Even though the name is send bit, it's actually not being sent during this state. It's already sent over here. Okay, it's already sent over here. But the send bit state will look at the index. If you see the index is already reaching 9, because there are 10 bits, right? It's already reaching 9, it's still fine. But after the 9th bit, after the bit 9 or the 10th bit, it will be incremented one more time, and when it comes back to the send bit, this will not be satisfied anymore. It goes to this one, will go back to ready, right? So be ready for the next message. But if it's still not reaching bit 9 yet, you can see it keeps going back to the low bit state to do what? So the message has 10 bits, right? So it's taking out one by one. So every time it do the low bit state, it takes out one only, and then counts up to 1 over 9600 second, right? To form that 9600 baud rate. It takes out one by one, right? If it's not reaching the 10th bit yet, it will come back to the low bit state to do what?
Get another bit.
Yeah, to get another bit, right? And then keep doing that. Once it reaches the 10th bit, it goes to ready for what? It goes to ready for what? For another what?
Another TX bit.
Another message. Okay? For another message. Because the ready state is waiting for the send command to form a new message. And how the message is being updated. You got data here. How this is being updated. Hey, I just come back to the ready state. I want to start sending another message. How could I make sure that the data is a new data or new message? Anything is a control layer over here. Which layer is a control layer over here? The send. The send bit is a control layer. If it's not satisfying that state, it won't get into the next state. So the send command is from the top. The top is sending messages to it. if there's there's no new message, it wouldn't assert your send bit, so it wouldn't start loading the new data to it to the message and go to the next state, right? So the top layer will make sure that there's the new message. There's a new message, and then if I have a new message, I will assert the send bit. So the sub module, the TX control module, will be able to form a new message and move to the low bit and send bit states, right? So the question is how the top can know that if the message has already been sent, so it's ready for the next message. How could the top know that? So just imagine what's really happening, right? So the sender, the TX, the TX receive a data is in parallel, right? It's in parallel. The TX control module, right? Data, that's from the top, right? And so the role of the TX is taking the 8-bit data and form it and put a 0 starting bit and stop bit here, right? Just adding to the data to form a message and send out every single bit to the TX port one by one, right? Because it's a serial port. You don't have a parallel data output, it's serial. So the whole point here is to make everything serial so it can take less resources of the pin resources of the chip, right? So parallel to serial. So like boom, 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 like this, right? So you have a top, and the top is so the top's role for our experiment, not for the other communications, right? Just for our experiment, the top's role is going to update. It's going to update all the data over here. Okay, make sure that whenever this is done, I'm going to load a new data here, and so it's able to do a new data transmission, right? How could the top know that this guy is done? So I'm not loading it whenever this is still doing the job. It has to finish first before I load the new data. Otherwise, it's just reaching bit 4, and then everything got changed. It's getting updated. It's a disaster, right? I want to wait until this is done, and then I load the new data here. Otherwise, you are keep updating it, but you are sending the wrong data. You are not finishing one yet. You are sending another one, right? How could this know? How could I let it know? Just make it very simple, right? Just send a message to it, right? It could just be for the state whenever it's ready. During the ready state, I want to give a little command here. I could call it ready. Right? If the ready is 1, so I can have a date. I have a register type here. Also call it ready or something. Right? So in your top module Verilog, you can keep looking at this ready. If this is ready is 1, if this is 1, I load the new data to it. If 0, which means it's not finishing this transmission yet. So I just want to wait. So you can see how did we do that? You can see when. So the question for you guys is, in this sub module, when should we assert this ready flag to the top? When? At which state? Should be the very last state, right? Should be at the very last state. And in the very last state, we have a send bit, right? So the very last state is already almost reaching the last bit. Whenever it enters this one, enters the last bit. Then how do we give a 1 to ready? It's not giving a 1 to ready here, to the ready flag, right? So where's the ready flag? The ready flag is basically a register type. It's the output. It's actually just a port. Okay, it's the port. The ready, right? See, ready. This is the variable ready. But when we are looking at it, hey, whenever the transmission is done, which is reaching the max index, which is bit 9, right, the 10th bit or bit 9, it's going back to the ready state for the next message. But it's not messaging the top for the completion of the transmission. Where it is being asserted, then it's here. See, it's outside of the always. It's outside of the always. It's a combinational connection. So because everything, the snapshot, the hotwire snapshot, whenever the ready state, whenever the state is ready, so this parenthesis, when state equals ready, so which means this is true, right? When this is true, ready becomes true or becomes 1, right? Okay, so whenever it's steering the ready state, which means I haven't started the new transmission yet, but the previous transmission was done, I wanna just give a 1 to ready, which means it's ready for the next data. We're ready for the 8-bit data input to be updated. Does that make sense? Okay. So this one will be a little flag for the top. Now let's go to the top. Okay, go to the top. Here's the top. So before we go to the top, let's do a quick review for the debounce really quick. So what's happening, the outcome of this lab is, or not the outcome, but the result of the lab is, you open up the serial terminal, right? So serial terminal. And because your IPGA is being powered up and also doing communications through the USB, right? So when you connect it to a laptop, you basically just connect everything to the laptop through the USB port. And so it definitely has a serial in there because the USB has a serial, it's converted to serial, and you can have a terminal that can convert USB to serial as well. So eventually your serial port is able to communicate with your UART using TX and RX. There's a chip converting the data back and forth. We don't have to mess with it. It's already built in on both sides. So what's happening is the top will give a letter starting with the letter A. It's the ASCII code. Go letter A to the UART submodule, the TX controller first. And then sending that ASCII code to the laptop one by one. And it's incrementing that ASCII code one by one. So eventually we'll be able to show all the letters, uppercase letters from A, B, C, and so on and so forth. And after Z, it starts with the brackets and everything, all the other characters. And then start with the lowercase ones. It's just incrementing the ASCII byte one by one, right? So that's the outcome. So how it works is it's receiving a rising edge, actually the falling edge of the button. You have five buttons on the board, right? So it's using one of the buttons, actually is the middle one, the center button, center is the name of it in the constraint file. It's the middle button. When you press it, it gives a falling edge. And then it triggers a change. So you are looking at the falling edge of the button. So the question here is why it's forming a falling edge by pushing the button here. So I have to look at the hardware, right? These are the buttons. Are they active low or active high? Yeah, actually active high. So sorry, it's not a falling edge, it's a rising edge actually. So they are being pulled down to ground all the time. These are pull down resistors, right? So quick question, what are the resistance over here? Typical resistance over here and typical resistance over here. What are they? What are these? No, what are these? Hmm? I need some reasoning here. As you guys are seniors, you should answer this immediately in 1 second, right? I mean, be serious. Interviews will ask you these questions. So, especially the smaller companies. One of the students just got a job. I'm recording, so I couldn't say their names, but you know that, right? So one of the senior students just got a job in RF, right? I recommended him over there. So James Ferguson got a job many years ago and already taking a leading role over there and start requesting for more students from us, since no student can do things, right? And the interview covers everything, like from DSP to controls to digital circuits, IPGAs, semiconductor materials, controllers, VISIs. So smaller companies demands a lot more compared to bigger ones. You have to know things in order to get a job. So at least pretend to be an experienced electrical engineer. If I give you this kind of diagram, could you just tell me? It's just so simple, right? You guys shouldn't have excuse of not knowing this. So typical resistance for these, and the good reasoning for that. Okay, I'll just let you guys know, right? So even though there's no label of the resistance, right, but I can still tell. So one more question here. What about the typical resistance over here? What are they? LEDs, right? This is a current limiting resistor. What are the typical values? A couple hundred, right? Less than 1K. Otherwise, it's gonna dim the LED like crazy. So you want to keep several hundreds. Could be smallest probably 300 ohms. I mean, the higher end is probably 1K. You want to use a more than 1K resistance for the current limiting resistor for the LEDs, right? So what about here though? So these are pull down resistors, right? Pull down resistors. Doesn't matter is the pull up or pull down. They need to be high resistance. High resistance. 10K at least. 5K is a little bit too small. 1K is not good. So 10K. So before you push it down, this node is actually being directly shorted to the pin, right? So the pin is reading a what if you don't push it? The pin is reading a what? 0, right? Should be reading 0. And you want these to be a strong pull down resistors. So strong pull downs should be like 10K at least. 10K at least. Okay? And what about these ones though? These are for protection, right? Because whenever you push it, this pin, if you don't have this resistor, this pin will be directly shorted to the power, and there will be surges. Okay, will be surges, and the current will be too high sometimes. Since you don't know what the transistors formation is. So these ones are what? Just protections, right? So like these ones. So the protections should be what? A couple hundred, right? 300, 200, doesn't matter. So these should be a couple hundred. But the thing is, why these pull downs shorted to the grounds need to be higher, but the ones shorted to the power should be lower. So we are not pulling them up. We're not pulling them up. So whenever this is closed, when this is closed, right? This is basically you want this one to be shorted. So this guy, you don't want to drop too much voltage over this resistor. There's current running actually. So it's current running. So is there current running in here as well? If you push it, yeah, it's small, right? So that is why you need to keep them different. So if you have 10K here and 10K here, what's going to happen? Yeah, so you are losing a lot of current, right? And the voltage here will be half. Oh, is it half? Yeah, because there's no current running through. These are gates. Yeah, so that will be pretty bad, right? So you don't want any. You don't want them to be the same. So this should be small, so you are limiting the current, but not losing too much voltage. And these ones should be large, so we can have a solid pull down to ground. Okay, and so the thing is, you are detecting a rising edge, right? Detecting a rising edge, and that has to be written into a code. Okay, and because it's a switch, you push it, so that it's going to bounce back and forth, so you need to debounce to form a clear rising edge. Again, it is this code again. Let's understand this in an intuitive way, because there will be a quiz on Tuesday about this. I'll just let you guys write it, right? So unfortunately, I think if you want to prepare yourself really well for interviews and other things, you have to memorize something. It's like become a medical doctor, right? So you have to memorize a lot of names, the bones and blood vessels, nerves, all these kind of things. You just have to memorize something. But understand it, memorize it. Definitely, if I give you infinite amount of time, if you understand it, you can still write it down or finish it. But during the quiz time, it's probably only 15 to 20 minutes, right? So you guys should understand this block first, and then try to memorize something and prepare for the quiz on Tuesday, right? I'll just let you guys write up this debounce module. So why it is being coded in this way? So the structure over here, so when you sort of understand it in an intuitive way, is that when you push the button, right? When you push the button, it's going to bounce back and forth like this. And after a certain time of delay, it pulls up because it's a rising edge. You already saw the circuit diagram. It's a rising edge. Right? Eventually it becomes 1, right? However, it bounces back and forth. So what we can do is if you look at the data flow, right? So the data flows from a button. So the button is the input. See? The button is the input. And button clears the output. And this should be the same. But the thing is, this one oscillates, right? This one oscillates. So to avoid the oscillation, or we call it debounce, to debounce it, what we do is we assign this button value, even though it bounces. We assign it to a temporary intermediate variable called x new over here. Okay, so the data flows like this, goes from button to x new, and then goes to button clear, like what I described over here. See, button, x new, and button clear. So button clear is a clear rising edge from the output that we need. Okay, so it flows that way. So the thing is, it's always checking if the button and button new are the same or not. You are saying, hey, this is assigned to x new. This should be the same always, right? Why they could be different? Because it's bouncing, right? It's bouncing, so they could be different at the moment. However, whenever they are different, I force them to be the same. Does that make sense? I force them, whenever I detect the change, I force them to be the same. And whenever the next rising edge arrives, which is controlled by the 100 megahertz clock, if they are different again, I force them to be the same. If they're different again, I force them to be the same. Another very critical movement or step you need to do when you force them to be the same, what else you need to do? Clear the counter. Okay, clear the counter. Whenever I detect the difference, I clear the counter. I start timing again. Because it has to satisfy a certain amount of delay over here in order to not keep monitoring that anymore, okay? But during that time delay, if it's shorter than the time delay, if they're different, I force them to be the same. I clear the counter, clear the timer, right? Make sense? Okay. However, if they're not different for a certain amount of time, it reaches this point. So the counter equals the delay. Okay, so during that time amount of delay, it's not, I didn't detect any difference. What I want to do, assign the temporary data being stored in X new to button clear. So the condition is satisfied. I just give it out, which means I assume that if during that amount of delay, the debounce is, or the changes of the signal or the oscillation is not happening, I know that it's already stabilized. Okay, so I will just directly assign that output to X new from the temporary intermediate variable to the output. So that's what this happens. That's how this happens, right? And you have to increment the counter. If none of these are satisfied, just keep counting, right, as a timer. So given that, if we have this kind of structure or a debounce module, it's able to clear our rising edge and make a super clean rising edge, and we can directly use that rising edge as a signal, right? See, we are using the center button, the button center goes to debounce, and this one is clear, giving a clear rising edge. The clear rising edge is being used for increment your data, right? Increment your data. It's not part of the UART design as a universal UART design, because it's just for this demonstration that we do need to increment our ASCII code by using some kind of a triggering signal, right? So you can see the differences over here. So it's not just a static data output. You keep pushing it, you push it once, increment it once, and send a new data to the UART. So you can see it from the terminal. Okay. So here's the top. The top has an initial string, which is 41. It's not 41, it's 41. It's a hex. So 41 is a ASCII code for letter A. So initially you give a 41 to it, so it's outputting a letter A to it. And every time you push it, see, whenever the button clear has a 1 and the previous button was 0, so it's a rising edge detection, it's an edge detection. Whenever both are satisfied, it's edge, rising edge, it goes to the next state. Otherwise, don't go to the next state. Just waiting for what? Waiting for the push. Okay? Waiting for the push. So for the next state, you give a first letter to it, and then you increment the index, or you increment the ASCII code, because you do a A plus 1. Remember, A plus 1 is what? That's weird, right? What is A plus 1? We did it in microcontrollers, right? Remember, what is A plus 1? B. Right? Isn't A plus 1 a B? Yeah, it's ASCII code, right? ASCII code. So A is a character. You can directly add a 1 to a character, even in C, right? In C programming and microcontrollers, you can also do a A plus 1. It's going to give you a B. It's incrementing your ASCII code. It's just a feature of the coding, right? The same here. So the compiler was the tool, Vivado, is able to recognize the A here, because we are giving this ASCII code. This is actually a hex, right? The hex. So we are sending a hex, which is ASCII code, but your monitor, your computer can recognize that byte and convert it into a letter, right? Okay. So a quick, simple question, right? A quick, simple question. So when you are sending a byte, it's being recognized as a character and displayed in your monitor. So what about you really just want to send a byte or binary? Could the monitor still display bits instead of a character? So if I just want to send a 1, binary 1, is that possible?
Wouldn't it just show a hex 1?
It's going to show a hex 1, right? It will be like 15 zeros and 1. Because all the UART protocols, they're only taking a bytes or bytes, right? So maybe a hex 1, and then you have to modify it using a mask or something in your C to extract that bit. That make sense? Okay. So it's always sending bytes by bytes. These are all ASCII code, right? Okay. And during the button send, whenever it's getting incremented, it goes to the next state, right? And then if it's ready, we I think I found out a little bug over here, but so some of the states, so this state is not necessary, I remember, but it's not really making any difference. Let me see. So if here, whenever I send A and increment it, and then go to go back to here, right? Go back to here. So it's ready for the next one, right? Ready for the next one. What about this guy though? Button send wait. Button wait. Button send. Button send wait. Button send wait. It's not even jumping to this state. Right? So this is an example from the textbook. I don't think it's ever entering this state at all. You agree? Do you see this state anywhere? So this is totally redundant. It's not doing anything. So this is unnecessary, okay, from the example. But all the other ones are working, so you can use them and make it work that way, okay? And so the next Tuesday we'll talk about the receivers. Got a top here as well. And you can start working on several tasks. I mean, task 1, at least. Okay, so let's take a look at all the questions from the in-class, right? So the first one, what signal does transmission? So this is simple. And the second one, not a problem. Third one, no problem. Fourth one, what does it put down the transmission line? So this is the question about the concatenation, right? So it placed all the byte in the middle and put a 0 and 1 to wrap it. Number 5. We're gonna talk about that. Number 6. 115 installation. Okay, so this one we didn't cover. Let's go back to that one. So here is a hashtag with a parenthesis, with a magical number over here. So the thing is, you see the variable called baud, right? The baud in the sum module. To be honest, this is being used very often. So this is a very common technique in Verilog. So you can overwrite the baud rate. So in your sum module, right? In sum module, we have a parameter. So keep in mind, if you declare that variable as a parameter data type, and you can override it. But local parameters cannot be overridden, right? But the parameter can be changed. So the parameter variable, which is called baud, we define it as 9600. However, in your top, you can use a hashtag with a parenthesis to override it. The question is, how do you know? You didn't say anything about the parameter, right? How to know that this is overriding that parameter, not others? How? See, you instantiate it from the in the top as a sum module, and then you have this little thing here, and I'm telling you that this is overriding the parameter variable in your sum module. So my question is, how it knows that? Or how does it know it's overriding the 9600?
It's just the placement.
It's just a place. It's depending on the order actually. So when you declare it, so for example, this, I mean, for this case, this is the only one parameter in this sum module, right? So it's the only one to replace. But you have several ones, it's going to replace everyone in a certain order. It's from the top to bottom. So the declaration of the parameters data types, they have to follow a certain order, depending on your top, right? So if the top, you override it, you have to look at the order like they are being declared in your sum module. Okay? And then you have all the connections over here. And then something else. This is a parity bit. So we'll talk about this next Tuesday. It's a bit too overwhelming to do everything today. All right. I will let you guys take a look at it really quick, and I'll come back in 2 minutes to talk about the other questions I have on the in-class, right? A couple other questions to finish. Now let's see. Number 6 in the UART TX top module, line 15. Oh, that's the override, right? So override as a bar rate. Number 7, explain how that works. Line 37 from the top module, top TX module. Let's take a look at it. Here, 37. Here, right? So we already talk about that, right? Whenever this is 1, whenever this is during the send state, I give a 1 to send, right? So I give a 1 to send. So start sending. Otherwise, it's a 0. Why is that? This is the top, right? The top for TX. So you can see here, the button send state is actually this state. Okay, it's this state. If this is the 1, it gives the 1 to the flag, which means it's not ready yet, right? Whenever it's ready, this is 0. So in that case, wait, let's go to the sum module and see. UR send is shorted to where? To send. UR send is given to send. So the thing is, send has to be 1 from the TX module to start the new transmission, to give a new message, right? To give a new message. So let's see, does that make sense? I'm also thinking about it. Does it make sense? So during this state, I give a 1 because I just have a new, I just give the character to the data, right? So in that case, I want this to be 1. So your sum module, the TX module, is able to receive that send 1, the 1 to the send command, and we'll start doing the transmission. We'll take it in and do the transmission. But the thing is, it happens really fast, right? See, because every time it enters this state, there's no condition. It just does this, and then immediately the state becomes next. So the thing is, it's just 1 clock cycle, actually, from this 100 megahertz clock. So only 1 clock cycle. It enters this state, it gives the new ladder to this data, the 8-bit output, and then the state got changed, which doesn't matter because the data port already received the new data. It's already there. It's only wait, so it goes back to this state, only wait for new push, another push to come back to this state again, to update the input, right? To update the input data, which makes sense. It's only 1 clock cycle. And that clock cycle will give you a really quick send signal, and that send signal will immediately take in that 8 bits. See? When send is 1, the clock cycle is being synchronized by the same clock rising edge. We'll directly take it in and put it over here. All right?
So then, how does this line 37 work if it's like outside of the always block? Like, how's it gonna know?
Yes,
It's
always.
constantly checking because it's not inside always.
It's just a wire connection.
Okay.
So the thing is, whenever this is the 1, this becomes 1. There's no control. It's just directly combinational or just wire.
Okay.
It's not being synchronized. It's not synchronized to the clock. But when the clock updates everything, it's directly updates because it's just a wire. That's a good question. So think about that. So whatever I just described will be the answer for question number 7.
So it almost is tied to the clock then because it's a wired.
Yes,
Okay.
it's a wire, but it's not being driven by the clock, right? It's just updated by the clock. Whatever within that always block being updated, this will be updated as well because the state is getting changed. So number 8. We're not there yet. Number 9. Yeah, okay, I guess we'll have to cover that on Tuesday next week. So already too much stuff to be covered today. Let me see. Take another look at the deadlines. Any question on the deadlines before we have any other issues? I'm sorry for the last one, but just let you guys know whoever came late. So first, try to become on time, and second, the homework 4 was due on Thursday, was due on Tuesday, and I think I updated over here. I was trying to push it to Tuesday next week, but the thing is already due Tuesday this week, right? If you are still working on it, you can keep doing that and submit it. It won't be considered as a late work. So this will be due actually Tuesday next week. So hopefully you guys can have some time to work on the LCD assignment. Like I showed you guys.
Quiz on what day now?
Yeah, quiz on Tuesday.
It's just the module.
The module, yeah, it's just debounce. Okay, just debounce. Tuesday next week, the debounce module. Okay.
It'll just be writing the debounce.
It's better than debounce, yes. So understand that first, right? Understand that first. It's always the data flow is from button to X new and then to button clear, right? And then waiting for a time delay. So it's the major part. If you have other declarations like register types and other wires and the ports are not perfect, which will be fine. I wouldn't take points though, but the major part should be correct. Okay.
So we will do a little bit of the diagram?
No, just the code.
Okay.
Just memorization.
I see.
Would you like some NVIDIA interview questions in the future, I can put on a quiz so you guys can get trained on that as well. We'll take a look at it. We'll search online. Give you some heads up first. Okay. Imagine if you have all the homework assignments and quizzes are NVIDIA questions for the whole semester. You guys are ready for the job, to get a job from NVIDIA immediately after the semester. That's amazing. That's going to be amazing. I should consider that. All right. Any other questions? LCD. I showed it to some of you guys at the very beginning, but other people were late, so we didn't cover that for you guys. I worked on that for a couple hours, and the result I got was just there's no internet right now. So I was able to do a simple, very simple unsigned addition, but you guys need to modify it and start from the template and use the tools complement, add subtraction functionalities, signs, and increase the refreshing rate so it's not blinking all the time. And that's it. Okay. All right. See most of you on Tuesday.